I'm very happy to be here, even if I feel like an outsider to the subject of the main of most of the talks up to now. So I will talk about a joint work with Steve Herder from University of Illinois at Chicago. This is a project that has been on for a very long time now. So I will spend a lot of time explaining to you the things the things that were done before we started. And then at the end I will talk about a little bit about our results, and please stop me in the way because I like to be stopped. So I put generic, so let me start by telling you what I think. The title in the abstract is not Cooper-Rock plug but flow, but I will explain you why it's the same. And let me start by just telling you what Christina Cooper-Rock proved in '94. And then I will come back a little bit to the history of why this problem was important. But I start in this way. So if you have a closed three-manifold, then the Euler characteristic is 0. So you can always find vector fields without zeros on it. And then you ask yourself whether you can find examples without periodic orbits. And the answer is yes. And I will try to show you how you prove that. Okay? So there are C-infinity. I will work on the C-infinity case all the time. You can do it real analytic. It's not in Christina's papers, but you can do it. And you can prove that there are no periodic orbits. So let me see. So this is a citation from Henri Poincaré that says that periodic orbits are the only path to understand places that we haven't never understood. But this is obviously more than 100 years old as a citation. Okay. So the way you prove this is using plugs. So let me just tell you what a plug is quickly, and then I will pass to the definition. So suppose that you have a periodic orbit, and that is isolated. Let me think about that for a moment, and then I will tell you that always exists. And you want to break it out. So the idea of the plug is to pick a point in the periodic orbit, and then you know that around that plug you can find a neighborhood where the vector field is trivial. And then you will erase the vector field inside the plug, inside this flow box, and change it for something. And the idea of changing it for something is that this point, its orbit will enter the plug and never leave. Okay? And so you're breaking the orbit. And you want to make it in such a way that you're not creating new periodic orbits. Okay? So a plug is going to be a three-manifold with boundary, and though with a non-vanishing vector field, obviously, because I don't want to get out of the vector fields that have singularities, where you're going to change the vertical vector field for something. And here there are periodic orbits in that drawing, obviously. But the breakthrough that Christina managed is to do a plug without periodic orbits inside. And if you want to do that process and not create periodic orbits, you have to do two things. One is to ensure that there are no periodic orbits inside the plug. And one is that you're not creating new periodic orbits. It's by saying that if you have another point whose orbit arrives here, okay, so it comes from somewhere, it arrives here. I told you this periodic orbit is isolated, so this is not in a periodic orbit. But I want to assure that when I do this surgery, I'm not creating a new periodic orbit. And how do I do that? Well, this orbit used to exit exactly in the point in front of it. Okay, so I will do it such a way that the orbit might be very complicated inside, but when it exits exactly in the point in front. Okay, so a plug basically has those, I didn't wrote it down, but it has this, so it's a three-manifold with a non-vanishing vector field that you can embed, preserving this vertical direction, that has points that enter the plug and will never exit. So these are the trapped orbits by the plug. And if an orbit is not trapped, then we will exit exactly in front where it came in. Those are the things you want. And if you can build a plug without periodic orbits inside, then you can change any vector field that has isolated periodic orbits for a vector field that has no periodic orbits. Yeah? Okay. So Christina Cooper constructed a plug without periodic orbits. And one of the things that was never studied is that if you take one of these trapped orbits, it has to limit to some invariant set inside the plug. And so it has to be a minimal set. So a plug, you can also see it as a way to insert a minimal set into your flow. Okay? And what we did was to study this vector field, this minimal set. So let me tell you a lot of the history of results behind the theorem. So in the 50s, Seifert proved a very nice theorem. So if you have S3, you know, a nice vector field that was cited yesterday. So you have the half vibration, and you can take a vector field that is non-vanishing and is tangent to it, and all orbits are periodic. And what Seifert proved is that if you have a vector field that is C0 close to this, it will have periodic orbits. And then it said, well, maybe it's true that any vector field on S3 has periodic orbits. Why did he said so? Because we know that if you want to find a non-vanishing vector field, there is a topological quantity that tells you if you can do it or not. That's the other characteristic. So in some sense, there was the spirit of finding some topological quantity that, or invariant that you can associate to a manifold that will tell you this manifold accepts or it doesn't accept a vector field with periodic orbits. And that's impossible. That doesn't exist. That's part of what I want to tell you. So he asked, well, maybe all vector fields, all non-singular vector fields on S3 have periodic orbits. And this became known, the positive answers to this became known as a Seifert conjecture. Okay. Then in the 60s, Wilson built, to my knowledge, the first plug. There is a plug that has periodic orbits, has two periodic orbits, and it traps a lot of orbits. And with this plug, he can build on any three manifold a vector field that has two periodic orbits. Okay? Just the two periodic orbits are in the plug. Okay? And he also, the same plug, solves a problem in higher dimensions. You can change, well, he did it. He changed a little bit the construction from 3 dimensions to higher dimensions. And in higher dimensions, you get a plug without periodic orbits. So he solved the problem for higher dimensional manifolds. If you have a manifold that has dimension bigger than 3 and has Euler characteristic 0, then you can build a vector field without singularities and without periodic orbits following Wilson's constructions. There's other constructions in higher dimensions, in dimension 3. The only known construction is Christina's construction. Then in the 70s, Schweitzer managed to change Wilson's construction and get rid of these periodic orbits inside the plug and change it for a minimal set that we know very well in foliations, that is the Danjois minimal set on the torus. And that gave him a plug without periodic orbits with the problem that the vector field is only C1, and you cannot make it. You can make it a little bit better, you can make it C2. Jenny Harrison did that in the 90s. And that's where it stops. And then there's some amount of effort to prove that you cannot do its infinity between Schweitzer's results and Christina's results. There's a couple of papers that try to prove that you cannot do its infinity, even if now we know that we can do it. So one of the main things of Wilson and Schweitzer's construction is that you start with the minimal set and you build a plug around it. And in the Wilson, the minimal sets are periodic orbits. In Schweitzer's, there are 2 copies of the Donjois minimal set. And in Christina's construction that I will explain you in a moment, you do it the other way around. You build a plug and you don't have no idea what the minimal set is at the beginning. So just to complete the results, let me cite Greg Kuperberg proved Wilson and Schweitzer result for volume preserving vector fields, also using plugs in a very different way. Though. The problem of whether there are C2 examples without periodic orbits that preserve volume is completely open now. Okay. Okay. So let me come back to this. So as I said, these vector fields don't preserve volume. They cannot preserve volumes. And then there is the other side of the problem is if you have a vector field or flow in tree manifold that is non-singular, you can ask, for example, if it's a Rab vector field, or if it's geodesical, or if it's acts by isometries, or something like that. And you can say, well, maybe those have periodic orbits. And the answer is yes. So there is some limit. I mean, there's these examples without periodic orbits, but there's a bunch of families that all have periodic orbits, and we know that. Okay? Okay, so let me go to the construction. So there's a easy part of the construction, and there's a complicated part of it. So start with a rectangle and draw a vector field like that, any vector field. So in the middle vertical line, there's 2 singularities. It's always going up. And think of the middle horizontal line. It has to be antisymmetric with respect to that line. Okay, it means that top bottom you have the same vector pointing upwards. And then you multiply this by S1. And when you multiply this by S1, you get a fat cylinder. Maybe another marker. Yeah, sure. Thank you. I will just do part of the boundary. And then you want, so that's called W1, that's what I wanted to say. And you want to define a vector field here. And you will take that W1 and add something in the theta coordinate that depends on a function. And that function is defined on the rectangle. And it has values, let's say, on -1, 1. But you can choose whatever you want, symmetric interval. And what I will ask is, so I want to use this. This is a plug. This is going to be a plug with 2 periodic orbits. Okay? It's the first step in the Kuperberg construction. We have 2 periodic orbits. Sorry. I moved this. So what I want, since I want to insert this in a manifold that already has a flow, I need the vector field to be vertical near the boundary. So I need that F to be 0 near the boundary. So that's the first condition. Okay, I will ask F to be 0 near the boundary of the rectangle. Okay? Then I want to get rid of these singularities because I want a non-singular vector field over there. So I will ask F of P to be equal to 1 and to be equal to minus F of Q. So that means that there's a first periodic orbit that goes around in one direction. And there is a second periodic orbit that goes around in the other direction. Okay? I can stop, I can say it, so just stop me if I'm going fast.
Can you change to the blue mark?
Yes. And the orbits should be basically the same size. So. Okay.
I'm just going to make sure I'm understanding. If I I think of this as a solid cylinder and I'm using cylindrical coordinates, is this vector field just depending on r and theta?
Yes and no. Let's say r is here.
Oh, that's the r, okay, yeah.
Yeah.
All right.
Theta is a new one, but there's a c coordinate that has to, I mean, it depends because it has to stop. Okay? But yeah, you have all the cylinders, the theta constant cylinders are invariant.
Yeah.
That's true. Well, then you have this point whose orbit goes and accumulates on P, and that gives us a circle here in the entrance where if I start with an orbit, well, at the beginning the vector field is vertical, but then I start to get to places where this function has to be positive, and so it will turn and accumulate on the first periodic orbit. Okay? Yeah? And the last thing, so far what I asked to the function is to be 0 near the boundary, to be 1 in the first singularity, to be -1 on the second singularity. And the last thing that I will ask is to be antisymmetric with respect to this middle line. And why do I want that? Because if you take a point that is not in the circle, its orbit is going to go across the plug, because that vector field is always going up, so the orbit will never stop of going up, so eventually it will exit. And I want it to exit exactly in front of where it came in. So since I asked that vector field to be antisymmetric and I asked this function to be antisymmetric, that is going to happen. So the orbit will start and go around, and then at some point it will hit this middle vertical line, let's say c equals 0, and then it will turn back and do exactly the opposite thing until it exits exactly in front of where it came in. Okay? That's a modified version of Wilson plugs. This is marked over there.
So which are the orbits that are trapped then? Just the ones
The orbits that are trapped are the ones that come in this circle. Okay, that's r equal 2. Okay? And there are 2 periodic orbits. And then there is an invariant cylinder that is bounded by these 2 periodic orbits. So as I said, the cylinders where theta is constant are invariant. This is going to be extremely important in the construction. When you're near the boundary, the vector field is vertical. And as you start to go to the middle cylinder, r equal 2, you will find the 2 periodic orbits, the invariant cylinder in the middle, and when you come in, you accumulate on the first periodic orbit. On the top, you have the opposite situation. Okay? So far, so good. And now we want to destroy those 2 periodic orbits. And that's a problem.
Is this Wilson's construction?
This is almost Wilson's construction.
How did you cope? So you get 2 periodic orbits on the whole manifold?
Yeah, the thing is, Wilson's construction is not trapping just a circle, it's trapping a big annulus. And so you do a compacity argument where you choose first you choose a lot of flow boxes, so in such a way that you will intersect all the orbits of the original flow. And then you manage to take 2 flow boxes and change it just for 1. And then little by little you get rid of them. And in the end you have an embedding, a very complicated embedding of a plug that traps all the orbits. But it has to trap a big set. And this one just traps a circle. So that's why it's a modified version of it. And this plug that I'm talking about is the second version. Wilson has 2 papers. The first version is a very complicated vector field, and then he simplified it at some point. And if you want to understand the higher dimension thing, basically what you do, instead of multiplying by S1, you multiply by a torus. And so instead of that periodic orbit, you have a torus. And in the torus, you can put an irrational vector field. And that gets rid of the periodic orbits. Okay. So let me come back to Kuperberg. So the problem is how to get rid of those 2 periodic orbits. And the answer is this. Well, so this is a quoting from Matsumoto's paper on the Kuperberg block. So when Christina managed to do this construction, she sent the paper, and the referees of the paper was Matsumoto and Etienne Gis, and they both wrote papers on the construction. But Matsumoto was translated maybe 20 years after that. So this is the idea. So what we're going to do, is to insert parts of the plug in itself, so that the plug traps its periodic orbits. Okay? Ready? Okay, so this is the difficult part of the construction. Okay, the first step is just to embed that plug like that on R3. Haven't changed anything. Okay, the vertical direction is preserved. And then think of the entrance annulus, so the annulus that is below in this plug, and looks a little bit like this. Okay, and I'm going to choose a lot of things. So first, remember that we have this is radius equal to 2. And those are the orbits that are trapped by the plug. Okay? So let me choose a small disk here that intersects this trap set, and choose a point. So D1, let's say, and this point, let's call it P1, and then choose an arc in front. Okay, and the first thing we're going to do is to insert no vector field. Forget about the vector field for a moment. To insert this disk inside the plug in such a way that this inner boundary is going to go to this segment, and the point P1 has to go up to the periodic orbit. Okay? So now if I erase a little bit of things here, I will put you the nice pictures on the screen in a moment, but let me do the picture little by little first. So this segment over here is some inner boundary segment in here, for example. And I want to map this point that I chose to a point in the orbit. And I want this disk, as I embed it, to be transverse to the vector field that is in here. Okay? And the vector field was vertical at the bottom, and it became horizontal little by little until the periodic orbit, where it's completely horizontal. So the disk is going to do something like this. Okay, where it comes, it enters, it goes up, and turns to be transverse to the periodic orbit. Once you inserted one disk,
Is that disk on the bottom?
it's on the bottom here.
Kind of from the bottom cylinder to the inside?
Yeah, and then I'm going to insert it in another part of the plug.
Okay.
Okay? So yeah, here is in the bottom. This is, I think I put -1 or -2. Okay, and then I'm going up. Okay? So fine, I haven't done anything. I haven't changed the vector field. Now push that disk with the flow a little bit. But here in the boundary, the vector field is vertical. So I will push it in such a way that it will exit over here. Okay? And then, so the end up of this thing is a disk whose boundary, this one goes like this, and the other one has to come like that. So this part of the boundary is tangent to the vector field of this region I just built. And then you have one disk in the entrance and one disk in the exit. Okay, so far I haven't changed the vector field, I just built this region. And now what you want to do is to erase the vector field that is there and use embedding to bring in the vector field that was over there. And that cuts the periodic orbits. And why I said this point has to go to the periodic orbit, because this is a trap point. And so I will hit the periodic orbit and the orbit will be trapped by the same plug. Okay? So let me show you some pictures, nicer pictures. So this is what I try to draw. I draw it myself, but with more calm. This is the region we built at the bottom, okay, for the first periodic orbit. And then what I'm doing is erasing the vector field that is in there and bringing in, let's say, the vector field that is in this part behind. Okay? So up to pasting, that's the Cooper-Root plug. I will give you another picture in a minute. And then you obviously have to do it for both periodic orbits. So you choose another disk, another point, and you do the same for the top periodic orbits. And if you look carefully, this region intersects the first periodic orbit but doesn't touch the second periodic orbit, while the second region touches the second periodic orbit but not the first one. Okay, so we can get track of what's happening. And then you do the surgery and you get this. Okay, so this is how it was embedded. And then you pull part of it and bring it to touch the first periodic orbit, and you pull part of it and touches the second periodic orbit. And that is the Cooper-Root plug. Okay? And you have to prove a bunch of things. You have to prove that it is a plug, so you have to prove that an orbit that enters and exits, it will exit exactly in front of where it came in. You have to prove that there are no periodic orbits, and then you can use it to destroy periodic orbits. Okay? Okay.
I think it's lucky that Wilson's argument worked in higher dimensions, because I think about how you do this.
In higher dimensions, yeah. Yeah, exactly. That's a good one. Okay. The vector field still being vertical near the boundary, because the boundary is part of what it was a boundary before. Okay. Okay. So here is a little bit of what happens inside the insertion. So you pull and then you turn. And so what it used to be the periodic orbit, now it's an orbit that hits here and will go to travel along the plug, but it won't exit to close the periodic orbit. Okay. I don't know what follows. Yeah, so there is one condition. There is one more condition that you have to ask. So I told you have to ask that this point goes to periodic orbit, and so that the periodic orbit is trapped. Well, you have to ask one more thing. So remember we had these cylinders that were invariant, radius constant. Okay, so that is the vertical line, is radius equal to 2. But when you get to the insertion, you will see a new radius coordinate that comes from the insertion. And you need to ask that except at that point that I chose that went to the periodic orbit, at any other point, the radius will grow when you hit an insertion. And this is one way to control things. And if you don't ask this, you cannot prove that there are no periodic orbits. This is only used to prove that there are no periodic orbits. Okay. So how you study the dynamics of this thing?
You mean trying to get a minimal set?
Yeah, information about the minimal set, or what are the invariant sets? And basically, everything is encoded in that picture. That is much simpler than the other one. The only thing you have to learn is that once you're here, you jump and you're over here, and then you follow the orbit, and then at some point you hit either an exit or an entry, etc., and you follow the orbit. So the orbits are made of pieces of Wilson orbits, and Wilson orbits are simple. So what you have to understand is how they concatenate. Okay? And if you want to use to study this minimal set, well, one thing is first to prove that there is one minimal set. Okay, and I will try to explain you why there is only one minimal set and not more of them. But what we want to study is these two special orbits, so the two orbits that contain what survived about the periodic orbits. Okay, so these are my special orbits, are the orbits that contain this arc of periodic orbit and that arc over there. Okay. And what is going to be important for us is that entry points now can be entry points to the insertions, and that when you enter a point, I want to follow what happens in the exit, and I will say that these 2 points are facing if they have the same r theta coordinates. Okay? So now you go to this main lemma, that if you have an entry point, and this can be not just an entry point at the bottom, but an entry point on one of these two disks, and the radius is bigger than 2, so you are in the outside part of the plug, then the orbit will exit at some point, maybe very long time, but it will exit exactly in front of where it came in. So it will exit with the same r theta coordinates. Okay? No, it's the same, yeah. Okay. Okay. So this is the cylinder r equal 2. And I will just try to explain you why there's only one minimal set. Okay? So if you remember, before doing the insertion, I had an invariant cylinder r equal 2 where the two periodic orbits were, and I had an invariant cylinder in the middle. And now I cut it because I did these two insertions, so I erase those two rectangles. And what happens to the orbit? So the first orbit that is in green, it hits insertion at a point, and this is the very special point that I chose to be a trap point. So it's a point with radius equal to 2. So this point over here is identified with some entry point at the bottom of this picture. I choose one. Then you follow the orbit. It might do a lot of turns, but eventually it will hit this thing. But then there is a radius condition, and that point has radius bigger than 2. And then you're happy because the lemma tells you that the orbit, I don't know what it's going to do, but eventually will exit here. And then it will continue doing what it was doing as a Wilson orbit, so it will make another turn, hit again, but again with a radius bigger than 2. So in positive time, this green arc will accumulate on the first horizontal arc. While if you do the same analysis in backward time, this point again has radius equal to 2. It corresponds to the facing point to this one on the top. And then you do the analysis backward. And this will always be hitting the insertions in radius bigger than 2, so you know what is happening. Okay? So in positive time, this green orbit accumulates on the first horizontal arc, while in negative time, it accumulates on the red horizontal arc. And now if you follow the red orbit, it does exactly the same. So these two orbits have, their closure is one containing the other. And now if you follow, if you do a little bit more of work, what happens between this point and this point, it gives you a sequence of points that have radius bigger than 2 but tend to 2 and accumulate on the cylinder that is bounded. I'm going to call the Reb cylinder. So they accumulate on the Reb cylinder, So you have some points of the Reb cylinder have to be in the minimal set. And the question is whether it accumulates on all the cylinder or just on a Cantor set. Okay, that's a difficult question. The other thing that I'm saying is this is the only minimal set inside the plug, the closure of any of these periodic orbit, of any of these special orbits. But that takes a little bit more of work to be proved, so I'm not going to prove that. The Reb cylinder is a cylinder is between the two. This is truncated by the insertions, but it used to be a cylinder bounded horizontal.
That used to be periodic orbit?
That used to be periodic orbit.
Is it a torus or is it a cylinder?
It's a cylinder.
So it's non-compact.
Now it's non-compact. Okay. Okay. So what I want to say with this slide is that the two special orbits have the same closure. And this is the only minimal set, and that I won't explain you why, but this is the only minimal set in the plug, and this was already known before we started working on this. Okay. So then this word generic that was on the title appears. As you saw, there's many choices in this construction. You can choose a lot of things. I draw things as if they were generic in some way. So if you choose the first vector field that I choose in the rectangle that had two singularities, if you choose that, the vector field to be quadratic, a quadratic function to the distance of these points, and if you choose this radius function to be, as I draw it, quadratic, then we can prove that these points that accumulate on the Reb cylinder accumulate on all the Reb cylinder. And so you will have a two-dimensional minimal set. Okay? I don't know what happens if you drop this hypothesis. I have no idea. I tried to build a plug with a one-dimensional minimal set, and I was not able to do that. But maybe it's possible. I have no idea. Okay. So now we want to, so the rest of the talk, what I want to try to give you is a picture of this minimal set. Because I like picture. Yes.
I got a little bit puzzled that you have some kind of a metric construction to help, but in the end, when you do the surgery and you insert, the manifold is topological. So is this some kind of artifact that you get rid of? Is it unimportant?
What is an artifact?
The conditions on the radius. Is something that you could, is it fundamental? Or?
It's fundamental. This radius condition, if you don't have this radius condition, not the quadratic, but if you don't have this radius condition that it grows, then there are periodic orbits. Okay. I can prove that. I mean, that's not so difficult to prove. The thing that is quadratic, that we had to put it in to prove something about the dimension. But yeah, the problem with this is it's a very topological construction. And then when you want to get to do some more things, you have to put some hypothesis into it. Okay. Okay, so let me just give you a couple of surfaces that I'm going to use to give you a picture of how it looks like, this minimal set. And for that, let me go back to the Wilson plug, so this fat cylinder with two periodic orbits. And take a curve in the entrance that doesn't hit the trap part, and follow it just inside the plug. So in the outside boundary, you know the vector field is vertical, so it just goes out. And as you go to the center of the plug, this thing starts to wrap around and eventually turn back and grab on the other side and exit. Okay, so what you get is what we call a propeller, but it's this tongue that turns around the cylinder. The invariant cylinder is bounded by two periodic orbits. And it's a compact thing. And now if you cut with some rectangle over here, what you get is a finite sequence of curves that this is the cylinder, this is the cut of the cylinder, that are near the cylinder. And if you have been unlucky and you cut exactly with a rectangle that passed through the tip, you will also have a point over there. Okay? Now, if you go now to gamma hitting the trap part, then you will get a non-compact surface that I don't want to close, so don't close it. Non-compact surface, it turns infinitely many times around the cylinder. And then when I cut, I will see an infinite amount of curves that are accumulating on this vertical line. Okay? And now I'm going to show you a little bit how it looks, this minimal set. So I'm going to choose a rectangle that I'm going to cut with, and I'm going to put what happens in the rectangle over there. And then remember we had this cylinder, and under this generic hypothesis, as we call them, this cylinder is contained in the minimal set. So what I want to do is to flow the cylinder and see what happens. Okay? So the first thing to see is that the cylinder hits insertion in curves that go from the boundary of the insertions to a trap point. Okay, so let me start with my drawings. So I will put the cylinder over here. So this is the cylinder with the two notches done by the insertions. And I will do just that. And I will forget about the rectangle. Okay. So now what happens? What happens, let me see, is that the cylinder is embedded something like this, but not really. Because the insertions, the cylinder has to pass through the insertions. Okay? So what I don't have is a nice picture of how that happens. So I have a non-smooth picture that tells you a little bit what that happens. That is this. Okay? So in the plug, in reality, you pull and you turn very smoothly. But I don't have a nice picture of that. So what I have is this. These were done by Joss Lees that helped me. And this cylinder comes tangent to the boundary of the notch that we erased, but just to the middle part of it. Okay? And now you want to flow this. So that's just how the cylinder is embedded. And this curve over here, the vertical boundary, if the flow is going this direction, let's say, the vertical boundary is a curve in the entrance of the insertion that goes from the boundary of the insertion to a trap point. So if you flow it inside of Wilson, forget about Cooper, inside of Wilson, it will give you one infinite surface turning around the cylinder. Okay? Now if you put it here, it looks like that. You have two surfaces, not really like this. I'm going to tell you why this is not true. But you have two infinite surfaces that will start turning around the cylinder. Okay? And let me draw it like here. So you have an infinite tongue that goes around, and it grabs around the cylinder. And it grabs both in the same direction. Okay? And they grab and they will make infinitely many turns. They accumulate on the cylinder. The picture is not correct in many ways, but one of the ways that is not correct is that these are like this. They are taking the cylinder inside them. If the cylinder is here, the transverse cut should be like something like this. But if you do that, you don't see anything in the picture. So that's why we did it like this.
This surface is oriented?
The surface is oriented, yeah. It's a cylinder.
What?
It's a cylinder. It's a non-compact cylinder embedded in a very curious way. That's what it is. Okay, so these surfaces continue to turn. they continue to turn, they become parallel somehow. But then at some point, maybe after many turns, but we just did it in the first turn, they will pass very near the insertion. And as they pass near the insertion, they will get a lot of notches, one each turn. And then on the other side. But then these have the nice quality that the curves where they hit the insertions have all points radius bigger than 2. So this will generate finite tongues that will go around. Okay? So this is what is happening here, and those tongues just stop at some point. Maybe after 100 turns, but they just stop. So you have this compact things coming out of here. And as you go down this, you don't see anything. They become, I don't know where the blue marker is. No, worst. A bit better. As you go down this picture, they become longer and longer, and eventually will hit the insertions also themselves, and we'll have branches coming out. And those branches will eventually be so long that will hit the insertions and have branches, and then you have a nice tree over there. Well, nice. Have a tree over there. And that's how the minimal set looks like. Okay, so now you want to say, I still have like 10 minutes. Now you want to say something about this minimal set. I have to move this here. Oh yeah, I forgot this. So this is a computer simulation of what happens near, let's say, on the top of that square or rectangle, there's this special point of one of the insertions, and this is how the two orbits hit the small transversal. This is a picture by Bruno Sebenek. And we now, I mean, they don't have any idea why they look like this, but we now can explain why you see the points like that. So nicely aligned.
I might be jumping ahead, but is this supposed to be kind of slice up the minimal set?
Yeah. Well, it's the minimal set in reality is curves that are going in the boundary of these sections, and then if you zoom in, you have more curves and more curves and more curves. Okay? But this is just the points in the orbits. So you have to closer, and when you close them, they get very nice. You get nice surfaces. Okay? Okay. So this is, let's say, to put it all together, if you have a generic Cooper plug, the minimal set is two-dimensional, and it looks like a stratified set. It has this two-dimensional strata. You can think it as the internal part of the cylinder. Okay, that gives you a nice lamination. We can give charts for it, all explicit. And then you have these two special orbits that give you a one-dimensional strata. And since it's minimal, it has to be dense in the two-dimensional strata. It has to be dense in the two-dimensional strata because it's a minimal set. I mean, that has nothing to do with it. And then we prove a bunch of things. So in the generic situation, the non-wandering set of the plug coincides with the minimal set. But there is a bigger invariant set. There is a bigger invariant set, but it doesn't contain any minimal sets. Okay? But there is a bigger invariant set inside the plug. And this is one of the reasons why the plug cannot be volume preserving. You can wonder about the entropy of this flow. So there is a big theorem of Katok that tells you that in 3 dimensions, if you don't have periodic orbits, the entropy has to be 0, because the entropy is bounded by the growth of the number of periodic orbits. Okay? But you can, instead of dividing, when you do the entropy, you look for separated points, you take the logarithm and you divide by t. If you divide by t by square root of t, or things like that, you are studying what is called the slow entropy of a flow. And for the Kuperberg flow is positive. Now the exponent depends on choices. It's not that we can say all generic Kuperberg blocks have, if you divide by square root of t, you get positive. But you can, for all of them, will be positive at some exponent, but the exponent depends on other choices. You could wonder what happens in a neighborhood of this vector field. These are very unstable examples. And you can wonder what happens in a neighborhood, C1 neighborhood, C infinity neighborhood, etc. What we proved is that if you take any C infinity neighborhood of this flow, you have not only one horseshoe, but a countable set of horseshoes. So you have a huge number of periodic orbits. And finally, Christina at some point asked us if we could study the shape of this minimal set, and there's something that is called shape theory, that I don't know if you know, that is studying a set that is embedded either on a Hilbert space, or in this case on R3, by studying sequences of neighborhoods that are shrinking to the set. And you study the homology groups, or the Hammurabi groups. So what we can prove is that the shape is unstable and doesn't satisfy some property that is called Mittag-Leffler. There is a bigger property that's called movable. We don't know if it's movable or not. Okay? And then you can ask me the obvious question that everyone, what about Hausdorff dimension? So there we have bounds on the Hausdorff, well, I didn't know. A student of Steve proved some bounds on the Hausdorff dimension of the minimal set recently. And then there are some other questions. And maybe the importance of this work is that this is the first explicit minimal set of a flow that is not one-dimensional. Okay? So, I mean, exceptional minimal, I mean, obviously not a torus. Exceptional minimal set of a flow that is not one-dimensional. And I will stop there.
An obvious question, which is the bound on the Hausdorff dimension, and also what does it mean that the strata are one-dimensional and two-dimensional? Which is the
So what I want to say by that sentence is, you could take, instead of taking the whole cylinder when I flow it, stop at an epsilon distance and flow that. Okay? That gives you a compact surface inside the plug, because that thing closes. It has a boundary, and its boundary is something that goes like this. It will go down, and then maybe it don't hit this insertion, but eventually go in, go out, and then etc., etc., etc. But you get a compact surface. Okay, so you can approximate, let's say, from the inside this minimal set by compact surfaces, and those are, then you can take, just erase the two special orbits, and then that's a lamination. It's Cantor, transverse Cantor, it's nicely embedded. Then when you get to the boundary, well, the boundary is not an invariant, obviously, because if not, it won't be a minimal set. And the boundary, it's accumulating everywhere. So let's say this piece of boundary will be this point here. Is very close to a point over here. And it's very close to a point in the cylinder. transverse. Okay? So that's why this picture is misleading for some things, because the embedding is so complicated that all these things are one on top of the other. And they're accumulating, say, radially on the cylinder and on each other at the same time. Okay? Is that clarified the second question? I call it the boundary, but it's not a boundary.
And the bound on the...
The bound is something like between 1.498 and 1.6 point. It's done with, so what he did is that, so what we have to study this thing is a pseudo group acting on a rectangle that tells you more or less where the orbits go. And what he could do is to interpret this pseudo group as an iterative function system. And then he used passing theory to find bounds on it.
Any other question?
I guess it's not volume preserving because when you reinsert this thing,
It's not,
volume or what?
it's not volume preserving because of the radius inequality. So let me just try to draw a picture. So let me draw just of the beginning rectangle in Wilson, just the bottom part of it, let's say. So somewhere over here there's a special point. This is going up, this is going up, this is going up. And then think that this is very near the insertion, so behind there is this other radius coordinate. So this is r, I think I call it tilde, r equal to 2. And then at some point you have the boundary of the insertion. So this is r bigger than 2, and here is r less than 2. Oh, sorry. So this was proved by Matsumoto. So now take a point in the entrance that has radius close to 2 but smaller than 2. And start flowing in the Wilson plug. So it goes around, it goes around, it goes around, and eventually it will hit the insertion. And here I'm fine, because this has radius as in this coordinates over here, it has radius bigger than 2. Now it will exit in front, turn around, and come in here. Okay? But at some point it will be very close to 2. And here the vector field is almost horizontal, so it's not doing anything. And when it jumps on the other side of 2, well, if it hits 2, it's trapped. But if it jumps on the other side, then you will be on a vertical line over here. And then you accumulate on 2. So there is some interval here where everything is trapped, instead of just one circle, as in the Wilson orbit. And that prevents it to be volume preserving. There's another problem that can be, the other problem is that the starting vector field of the Wilson is not volume preserving, but that you can get around it. But this is a big problem.
Time for one more question? No, let's thank the speaker again.